rate. In this chapter we will discussing about that the our exercise number of that. So first of all was what we are discussing about that the 1 mark question, then after 2 marks question, then after 3 mark question, and also we are discussing about that the 5 mark questions. So if further 5 mark questions are there, I will we will be conclude the see the how these our exercise examples how it will be asked in exam. So first of all, figure shows the capacitor made of two circular plates, each of radius 12 centimeters. Okay, and they're separated by a 5 centimeter. There the distance d, it is the 5 centimeter. The capacitor is being charged by external source, not so in figure. The charging current is constant and equal to 0.15 ampere. Is Kirchhoff's first rule valid at each plate of the capacitor? Here asking about that the each Kirchhoff's first rule is valid for the. So see here, yes, the Kirchhoff first law is true and valid for each plate of a capacitor because whether current flows toward the plate of capacitor in the form of conduction of current IC, same the amount of current flow away from it, the form of displacement current ID. We will discussing in the displacement current of ID. So this is the we are discussing about that. So Kirchhoff first rule is true and valid for each plate of the capacitor because of whether current flow throughout the plate of capacitor in the form of conduction current IC, same amount of current flow away from it in the form of displacement current. Now see here the second number is that a parallel plate capacitor made of circular plates, each radius is, see here again it is a circular plate, each has a radius is 6 centimeters, as the capacitance is 100 picofarad. The capacitor is connected to the 230 volt AC supply with the angular frequency. So see here the supply AC supply with the angular frequency E of 300 radian per second. Is the conduction current equal to the displacement current? What will be asked? What was asking that? Is the conduction current equals to the displacement current? Yes, we are already discussing the first example. What? There the conduction current and the displacement current will be same in the capacitors. So when we are, yes, when the current is the circuit change continuously periodic with the time, we have a IC is equals to ID. So it should be denoted that the conduction current IC flows in the external circuit in only up to the plate, where it is up to this plates of the capacitor, where the displacement current ID flows in the region between plate of capacitor. Then this between the two plate of regions, or that on that time it will be ID current. This is the displacement currents are there. So this is the phenomena is that basic phenomena. Now we are discussing about that the example number 3. Physical quantity is the same for X-ray wavelength 10 raised to 10 meters, 10 raised to minus 10 meters. Real light of wavelength is wavelength 6800 Armstrong, and the radio or wavelength is 500 meters. What the physical quantity is the same of X-ray of wavelength 10 raised to 10 minus 10 meters. Real light of the wavelength is 6800 Armstrong, and the radio wave wavelength is 500 meters. So all the given radiation have equal speed in a vacuum is given by c is equal to 3 into 10 raised to 8 meter per seconds. We know that. Okay, the light will be passing from this value of vacuum. On that time it has a, what will happen, it has a velocity is 3 into 10 raised to 8 meter per seconds. So here is the same statement. Actually this should have given at that all the radiation propagate in the same medium or propagate in a vacuum. If the radiation propagate in a different medium, then their speed would be different. Okay, while the propagating in the same medium, if their equal speed is v, then v less than c. Okay, so this is the basic phenomena that there are if the medium will be changed, on that time the refractive index will be changed, refractive index will be changed, the velocity will be changed. So this is the basic phenomena is that. Now A charged particle oscillates about its mean equilibrium position with a frequency of 10 raised to 9 Hz. What is the frequency of the electromagnetic waves produced by the oscillators? So, frequency of electromagnetic wave emit from a given source is always equals to the frequency of that source, and the so frequency of electromagnetic is represented in the case will be 10 raised to 9 Hz. Okay, a charged particle oscillate about its mean equilibrium position frequency of 10 raised to 9 Hz. What is the frequency of the electromagnetic waves produced by oscillation? It means that there are the frequencies 10 raised to minus 9 Hz. So on that time, what will happen? The electromagnetic wave will be also given source is equals to the frequency of the source. So there are also frequency electromagnetic waves represented case will be 10 raised to 9 Hz. Now see here another example is that the amplitude of the magnetic field a part of a harmonic electromagnetic wave in vacuum is B0, it is equals to 510. What is the amplitude of the electric field part of the wave? So nano during the propagation of electromagnetic waves in vacuum, if the amplitude of the electric and magnetic field we are representatively E0 into B0, where then C is equals to E0 upon B0 on the time. What will happen? What will happen? So B0 into C. So B0 our B0 is equal to 510 nano Tesla, 10 raised to minus 9 Tesla. So 3 into 10 raised to minus 10 raised to 8. So we'll get that the 1530 1000 1500 530 10 raised to minus 1. So we will get that the 1.53 into 10 raised to 2 volt meter inverse or Newton Coulomb inverse. So this is the value of A0. See here what will we get? The amplitude of the magnetic field a part of the harmonic electromagnetic wave in a vacuum is B0 is 510 nanotesla. What is the amplitude of the electric field part of the wave? So what happened? Electric field part of the wave. So on that time, how is the electric field are there? 1.53 into 10 raised to 2 volt per meters. Okay. Now see here in the example number 6, in the plane electromagnetic wave, the electric field oscillates sinusoidally at the frequency is 2.0 into 10 raised to 10 Hz, and the amplitude is 48 volt meter inverse. What is the wavelength of the wave? The C is equals to V into lambda. So lambda it is equals to C by V. So what we will get? The 3 into 10 raised to C is the velocity of light, and divided by the V it is the frequency oscillator sinusoidal frequency of 2 into 10 raised to 10 Hz. So we will get that the 1.5 into 10 raised to minus 2 meters. It will be 0.015 meters. Now we see here a plane of electromagnetic waves. The electric field oscillates sinusoidally at the frequency is 2.0 into 10 raised to 10 Hz, and the amplitude is 48 voltmeter. What is the amplitude of the oscillated magnetic field? Here it is the electric field. What we will get that the electric field is very 48 volt per meter. It is a electric field, and the C it is a velocity of light. So what will happen? B0 is equals to E0 by C. So 48 upon 3 into 10 raised to 8. So see here what we will get 16 into 10 raised to minus 8, it is equals to 1.6 into 10 raised to minus 7 Tesla. So Tesla it is the unit of the electric field. Now see here in a plane electromagnetic wave, the electric field is oscillates sinusoidally at the frequency of 2.0 into 10 raised to 10 Hz. Okay, the sinusoidal frequency is 10 raised to 2.0 into 10 raised to 10 Hz, and the amplitude is 48 volt per meter. So that the average energy density of the electric field equals to the average energy density of field. C is equals to 3 into 10 raised to 8 meter per second inverse. So see here the density in the electric field, rho it is equals to 1/2 epsilon 0 in E square RMS value. So this is the formula of the density of electric field. So epsilon 0 is equals to permittivity, and the energy in density the magnetic field it is equals to rho into B. Rho B it is equals to this phenomena is known as the rho. So we will get that the 1 half b square RMS upon mu 0. So we are taking that the ratio of this phenomena, we can get that the value of that. So rho e upon rho b, it is equals to E RMS upon B RMS square multiplied by E 0 epsilon 0 into mu 0. So what will get, c square plus 1 half 1 upon c square, it is equals to c is equals to 1 half epsilon 0 mu 0, it is equals to c square, it is equals to 1 half epsilon 0 into mu 0. So what we'll get is it is equals to 1. What we will get that the value is 1. So rho it is equals to rho of b. See here, rho of E it is equals to rho of B. So the electric field density of the electric field, it is equals to and density of the magnetic field. Now see here, the suppose that the electric field part of the electromagnetic wave in vacuum E is equals to 3.1 Newton per coulombs cos 1.8 radian per meters y plus 5.6 5.4 into 10 raised to 6 radian per seconds into t is equals to into I cap. So what is the direction of the propagation? See here equation of electric field as the form of like E is equals to E0 omega t plus k of y. What will happen here? It is equals to E0 is equals to E0 plus, see it is equals to E0, this is the value of 3.1 in Newton, it is the E0 cos omega t 1.8 omega, it is represented as a omega, and the t it is equals to 5.6 into k minus k minus y omega. So this is the phenomena like that. So and so given wave must be propagated all along y axis. Okay, see here it is a y axis. So see it is a ky and it is a omega into t. So this is the phenomena is the same as the electric field, same as the E is equals to E0 cos omega t minus k of pi. Now suppose what the electric field part of an electromagnetic waves in vacuum it is equals to 3.1 Newton per coulomb cos 1.8 radian per meters y into y plus 5.4 into 10 raised to 6 radian per. What is the frequency of wave? We see here with this phenomena we will be represented the omega. So omega it is equals to 5.4 into 10 raised to minus 6. So frequency it is equals to 2 pi mu it is equals to 2 pi f it is equals to omega. So we will get that the omega it is equals to 2 pi omega upon 2 pi omega upon f it is equals to omega upon 2 pi. So we what we will get omega v it is equals to 5.4 into 10 raised to 6 2 into 3.14 it is equals to 8.599 into 10 raised to 5 hertz. So what we will get the frequency it is equals to 86 megahertz. Now see here, suppose that the electric field part of electromagnetic waves, also this is also again these examples are there. What we need to determine what is the amplitude of the magnetic field part of the waves. Here we need to determine the magnetic fields of that. So what we'll get, C is equals to epsilon 0 E0 upon B0. So B0 it is equals to C0 by E0 by C. So we get that the 3.13 into 10 raised to 8. So 1.003 into 10 raised to minus 8 Tesla. So what will get that 10.3 into nano Tesla. Okay, now see here, suppose again we have another examples are there. Suppose that the electric field part of an electromagnetic wave in vacuum E is equals to 3.1 nano test 1 nano 1 3.1 nano coulomb. The cos it is equals to 1.8 radian per meter radian per meter into y plus 5.4 into 10 raised to 6 radian. So see here, suppose that the electric field of electromagnetic wave in vacuum is E is equals to 3.1 Newton per coulomb and the cos 1.8 radian per meter radian per meter into y plus 5.4 into 10 raised to minus 10 raised to 6 radian per second into t in the I cap. It will be in the x direction, so that's why. So now the equation for a magnetic field B is equals to B0 cos ky plus omega t into k cap. Okay, so we will get that the 1.033 due to this phenomena we get the value 1.033 into 10 raised to minus 8 t into cos 1.8 y plus 5.4 into 10 raised to 8 t into x. So this is the, if we take the direction of B along k, then only direction of E cross B it is equals to I cross k, it is equals to minus j, it is equals to direction of propagate of electromagnetic wave in the direction of minus y axis. Okay, so this is the I vector coordinates we are studying in the 11 science. So due to this phenomena we can get the value of that. Now, so the given below are some famous number of associated with the electromagnetic radiation in the different context in physics state the part of the electromagnetic spectrum to which each belongs to 21 centimeters wavelength emitted by the atomic hydrogen in the interstellar space. So given the radiation of 21 centimeter wavelength is in the section of radio wave, the electromagnetic spectrum towards the higher frequencies are there. Okay, so in the radiation wavelength is section of the radio waves. Now see here, the given below are some famous numbers associated with the electromagnetic waves. Different context in physics state of the part of the electromagnetic spectrum to which it belongs 1057 megahertz frequency of radiation arising from two close energy levels in hydrogen known as the Lamb shift. Okay, this is the Lamb shift. So we are Lamb shift we are studying in the 12th science or in the BSc or maybe in MSc. So there right now we are not studying this Lamb shift, but after that we will discussing the Lamb shift. Well, what is the Lamb shift are there. So in you are studying in the 12 maybe in a MSc physics or in a BSc physics. So given radiation is 21 centimeters, wavelength is 2. Wavelength is the section of radio waves of electromagnetic spectrum towards the higher frequencies. Now, given the see here, now given below are some famous numbers associated with the electromagnetic radiation in our different constants in physics. State the part of electromagnetic spectrum to which it belongs. 2.7 K temperature associated with the isotropic radiation filling all space through to be rally it to be Big Bang origin to universe. Now lambda according to Wien's laws are there. So Wien's law are lambda m into T. So there that is equals to 0.029 millikelvin. So we will get that the 20 meter into meter into Kelvin. So see here lambda m it is equals to 0.29 centimeter into Kelvin divided by 2.7 K. So we will get that the point is 11 centimeters. So lambda it is equals to 11 into 10 raised to minus 4 meters. So radiation with above wavelength is section of microwave of electromagnetic spectrums. Okay, it is in the electromagnetic spectrum. Microwave of the electromagnetic spectrums are there. So according to Wien's law, this is the Wien's law we will study in the previous chapters. Now see the given below are some famous numbers associated with the electromagnetic radiation in the different contents in physics. State the part of electromagnetic spectrum to which belongs the 589 Armstrong and 5896 Armstrong double line of the sodium. It corresponding to yellow colors in visible part of the electromagnetic spectrum. It is a sodium light will be it has a yellow line. So we are studying in the Newton's ring. These sources are used in the Newton's rings are there. So due to this phenomena we can get that the Newton's rings and we can measure that the wavelength of Newton's rings due to the Newton's rings. So now given below are some famous numbers with the electromagnetic radiation in a different context in physics. State the part of electromagnetic spectrum to each belongs to 14.14 kV energy to particular transition E F57 nucleus associated with the famous high resolution spectroscopy method Mossberg spectroscopy. Okay, so see here it is equals to we know about that the it is equals to h nu. So v it is nu it is equals to e upon this is the nu. Okay, this is a see here this is our nu. This is not a v, it is a h into nu. So nu it is equals to e upon h, it is equals to e, it is equals to 14.4 kilo volt, and it is a h it is our Planck constant. So we will put that the value of Planck constant 6.6 into 10 raised to minus 34. So what we will get the nu it is equals to 3.49 into 10 raised to 18. So we will get that the 3 point if we are rounding of this number we will get that the 3.5 into 10 raised to 18 hertz. So above the radiation is that the end of section of X-ray of is the beginning of the section of gamma rays. Now answer the following question. Long distance radio broadcast use the short wave bands. Why? Long distance radio broadcast used to short wave bands. So because in a short wave bands, radio waves of frequency 4.75 megahertz to 9.9 megahertz, whose very long distance transmission is possible by ionosphere. Okay, in the ionosphere this is possible to long distance traveling. So that's why we are taking that the short band waves, short wave bands. Now answer the following questions. It necessary used to satellite for a long distance TV transmission. Why? Long distance necessary satellites for long distance TV transmission. Why? So in order to send the radio waves to very large distance, we have to keep its frequency very high. Now radio waves with the frequencies greater than 30 megahertz are found to be penetrating the ionosphere, so they do not return to earth after reflections. So moreover, at higher frequency, ground wave propagation is also not possible. So because of very large amount of energy gets absorbed in this case, thus for a very long distance communication and for a converting entire surface of earth used to satellite is quite inevitable, compulsory. Okay. Now see the for answer the following questions. The optical radio telescope are built on the ground, but X-ray astronomy is possible only from satellite orbiting the Earth. Why? Optical and radio telescope are built on the ground, but X-ray astronomy is possible only from the satellite or orbiting with the earth. It means they are we can measure the optical and the radio telescope are on the ground, but X-ray are in the satellites. So because of earth atmosphere is transparent to radio waves and the visible light, but X-ray get absorbed by earth atmosphere. Hence we take the help of the geostationary satellite orbiting around the earth approximately at the highest height 36,000 kilometer for the study of X-ray astronomy. At this greater highest height, atmosphere is quite thin and so X-ray are not absorbed. Now see here, answer the